Hi students, now we are going to explain the projection of uniform circular motion on a diameter, and we are going to prove that it is also simple harmonic. What is meant by uniform circular motion? First of all, when a body is moving along the circumference of a circle with constant speed, okay? So here you can see one particle P. So let us take a particle of mass M is starting from the x-axis. So along the x-axis the diameter of this circle is xo x dash. Along the y-axis the diameter is yo y dash. Particle initially at a time t equal to 0, it is at x. Now it is going to revolve along the circumference of a circle with angular speed omega. Omega is constant. So after some time the particle will reach this position along the y-axis. So it started from the x-axis, now it has reached the y-axis. It should have taken a time equal to 1/4 of the period of revolution, because it is uniform circular motion. So the period of revolution is capital T, means 1/4 is T by 4. So we assumed that at a time T equal to 0 it started from the x-axis. So at a time T equal to T by 4, where it will be means at this position Y. Then after a time T equal to capital T by 2, so 1/2 of the period. So it will complete another quarter of a circle. Now it will reach the position x dash. Then again after a time equal to 3t by 4, the particle will reach the position y dash. Again after another t by 4, that is at the time t equal to 1 period, it will reach its initial position x. Can you see the initial position it has reached at a time t equal to period. So first you have to understand that the particle is undergoing uniform circular motion. Okay students, after it has completed one full circle, what next is going to happen? Again the same thing will be repeated again and again. This repeated motion is nothing but periodic motion, and we are going to prove that this periodic motion is also simple harmonic motion. Okay. So once again, let us consider the particle at a time t equal to 0. It has started from x, then here at t by 4, then here at t by 2, then it has reached here at a time 3t by 4, and it has reached here at a time t equal to its period of revolution t itself. Okay. Now I will consider the particle's position arbitrarily anywhere along the circumference. Say I have considered a particle at position P here. I join this outer circumference to the center, okay, so that the straight line OP is equal to the radius. OP is equal to the radius. So the radius OP I have taken, it is represented by capital A. A is the radius. Okay, now I am going to project the position of the particle P. I am going to project the position of the particle one along the x-axis at a point M, and I have projected the same particle along the y-axis, along the other diameter at a point N. So the projection of the particle on the x-axis is point M, and P is projected along the diameter yo y dash at a point N. So that at any instant of time, the particle P is having displacement along the x-axis, that is denoted by small x, and its displacement along the other diameter, that is y-axis, is denoted by small y. Okay. Now you see in this triangle OPN, you can see that angle. You can see that angle OPN. See here, O, this is P, and this is N. So that is equal to angle theta. Now the radius OP subtends an angle theta with the diameter x-axis, along x-axis. So this alternate angle also will be equal to theta. Then this height ON, so this ON is equal to the displacement of the particle y. Okay. Now you find out in this triangle, triangle OPN, in triangle OPN, what is the sine of theta equal to? Sine theta is equal to what? Opposite side by hypotenuse. So what is the side opposite to theta is ON. So this is equal to ON divided by the hypotenuse is what? OP. So sin theta is now equal to, instead of ON I am going to substitute the displacement y. So y divided by, instead of this hypotenuse OP I am going to substitute A. So this is A. Therefore the displacement y is equal to A sin theta. But here what is the angular velocity? Angular speed is omega, is it not? Omega, how will you define angular velocity? It is the rate of change of angular displacement. So omega is equal to theta by t. This implies, okay, this implies theta is equal to omega into t. Instead of theta I can also write what? Omega into t. Therefore this displacement y is equal to capital A into sine of omega into t. So this is the first equation. Okay, this is equation 1. This is the expression for what? The displacement of a simple harmonic motion, the displacement of SHM. We have projected the particle P on the diameter YO, Y dash, and we have determined its displacement y. So when the particle is at this position here, you see this picture or this picture, what is the value of theta? Theta is equal to 0. Is it not? At this picture, what is the theta? Theta is equal to pi by 2. At this point, value of theta is pi. At this point, the value of theta is what? 3 pi by 2. And again here when it reaches here, it is 0 or 2 pi. So theta is changing with time. At the same time, you see here, see when the particle is at this position, that is when theta is equal to 0, y will be equal to 0. And at this position, you see, at this position, y is maximum. So what is the maximum value of displacement here? That is equal to the radius. That is equal to the radius OP or A. Then again when the particle is coming here, the displacement is 0. Then when the particle is reaching here, can you see that the displacement becomes maximum but in the negative direction. So it is negative maximum. Once again when the particle reaches here, the displacement becomes 0. That means we have to understand that the displacement of this particle which is moving along a uniform circular motion, okay, the displacement of the particle is changing with time, and this change with the time is represented by a sine function, sinusoidal function. So what is this equation 1? Mathematically interpret the displacement of the particle is a simple harmonic, where A is constant, that is called the amplitude, and the maximum displacement called as amplitude. So we have proved that. We have proved from this equation that the projection of uniform circular motion or the displacement of the particle moving in a uniform circular motion is simple harmonic. Again, you must understand that in mathematics, a sine function, cosine function, minus cosine function, minus sine function, all these mathematical functions are called as harmonic functions because they will be repeated again and again in the same way or same fashion. So now you see equation 1 is a sine function. If I represent the equation 1 graphically means you see here now y equal to a sin omega t. So I will take the y-axis is displacement and the x-axis is equal to what? The period or time. Okay, the time. I am going to plot a graph between y versus t. Okay, children. Okay, at a time t equal to 0, what is the displacement t? You tell me. It is 0. So I will keep a pointer here. Okay. Then at a time t equal to t by 4, where is the particle? Here. What is the value of y? That is equal to capital A, is it not? That is maximum. So at a time t by 4, let us say that the particle, okay, here is the point. Then at a time t equal to 1/2 of the period, where is the particle now? You see here. So again the displacement is 0. So the displacement is 0. Then again here at this position t equal to 3t by 4, the position of the particle is negative maximum, is it not? So here maximum but negative. So I can represent somewhere here. Then once again when the particle at a time equal to 1 period, it returns back to the original position. So I can keep the point here. So I am going to join all these points, means what will be the shape? You can get the shape of a sine wave. In mathematics, this wave only is called as a sinusoidal wave, or shortly it is called as a sine wave. So since we represent the displacement of the particle in this uniform circular motion by the equation a sin omega t, we can say that it is a simple harmonic. Okay. So I can also represent here in terms of time. So this is time t equal to 0, this is t by 4, and this is t by 2, and this is 3t by 4, and this is after 1 period. So you can also project this, and you say that the amplitude, this is plus a, and here it is minus a. This is the amplitude. So this is y versus t, displacement. Okay. Next, how to find the velocity of the particle, velocity of SHM. So velocity is equal to what? Dy by dt, rate of change of displacement. So this is equal to what? D by dt of a sin omega into t. Okay, therefore v is now equal to, a is constant, so we cannot differentiate a constant, so it is taken out. In this product omega into t, omega is a constant but t is a variable, is it not? So d by dt of sin omega t. So this is a into d by dt of sin omega into t. So this is equal to a into sin omega t. When you differentiate, it will become cos omega t. But I told you omega is a constant, t is a variable. So once again we have to multiply by this coefficient of t. So I have to multiply with the omega. Therefore what is velocity? V equal to omega into a into cos of omega into t. So this is the second expression. This is for the velocity of SHM. So can you see the expression for velocity is expressed in terms of a cosine function. Cosine function or cos function is also what? Simple harmonic function. So the velocity of this particle also is simple harmonic. And what is the expression? Is v equal to omega a into cos omega t, where omega into a is the maximum of value of the velocity the particle can attain. Understand that? So this is omega into a is called as velocity amplitude. So I can write here omega into a. Omega a is called as a velocity amplitude. Okay, that can be the maximum value of the velocity that can be attained by the particle. Okay, now let us draw the graphical representation for the cosine wave. So cosine wave starts from maximum itself. So here at a time t equal to 0 itself, at a time cos 0, what is cos of 0, children? Cos 0 is equal to 1, is it not? So here cos of 0 will become 1. So that v will be equal to what? Omega into a into 1, that is omega a itself. So this will be the starting point at a time t equal to 0. Then it will attain 0 value. Okay. Then again it will be attaining a negative maximum. Then again it will attain 0. Then again it will attain positive maximum like this. So if you join all these points means what is the nature of the graph, you can see like this, okay. So that the graph will be like this. So appropriate scale if you take, appropriate scale measurements if you take means it can be still accurately. See here, below this I have taken this point like that, below this here at this point, okay, here like that, below this we have to consider another point like this, so that it will reach the maximum once again here. So you can project all these points by using a scale means the graph will be like this, that's all. So again we can write the time. So this is velocity versus time, okay. So here time 0 and here it is t by 4 and here, okay, this is plus a omega and this is minus a omega and here the time is what, t by 2, here 3t by 4 and here it is the period t. So from these two graphs we can see whenever the displacement is 0, velocity is positive maximum, is it not? And whenever here there is positive, displacement is positive maximum, here the velocity is 0. So there is a phase difference, there is a phase difference. This difference only is called as what? Phase difference. Now the next one, if you differentiate the velocity with respect to time, what you are going to get is called acceleration, okay. So the acceleration, next one is acceleration is given by, okay, you can take the symbol small a, this is equal to what, d square y divided by dt square, and this is equal to d by dt of velocity, is it not? So this is omega a into cos of omega into t. Omega a is equal to, okay, I can write d square y by dt square, the acceleration is equal to a omega is constant. Now cos omega t if you differentiate means it will become minus sin omega into t. That's the negative sign, is it not? So you take the negative sign with this constant out, minus omega a into sine of omega into t. Again this omega into t we have to multiply with another omega, so that this will become omega square a into sine omega into t. So this omega square a with the negative sign, this only is called as the maximum value of the acceleration or acceleration amplitude. So minus omega square into a is called as the acceleration amplitude. Now this also can be written as what, minus omega square into a sin omega into t. I am grouping the terms a sin omega t separately, so that a sin omega t is equal to what, in the expression 1 it is the displacement y. In place of a sin omega t I am going to substitute y, okay. Therefore d square y by dt square is equal to minus omega square into y. So this is equation number 3, which is an expression for the acceleration of SHM, where on the right hand side I told you already omega square into a, either whether it is a minus or plus term, it is called as the acceleration amplitude. Now we can complete the graph there. So at a time t equal to 0, okay, the acceleration will be 0. At a time t equal to t by 4, the acceleration will be negative maximum. At a time t equal to t by 2, the acceleration will be 0. At a time t equal to 3t by 4, the acceleration will be positive maximum, okay, positive maximum. Then again it will be 0 here at an instant t. So if you join all these points means you can have a sine wave which is in the reverse direction. So this wave is called as a minus sine wave, because here we are getting minus of sine omega t, is it not? Therefore it is the reciprocal of a sine wave. This is a sine wave, this is a minus sine wave, okay. Now what are all the points we have to write. So this you can write d square y by dt square. That is acceleration with respect to time. So at an instant 0, at an instant t by 4, this acceleration is a minus omega square into a. This is the maximum value of the acceleration. And next, at a time t equal to t by 2, it is 0. Then at a time t equal to 3t by 4, the acceleration is positive maximum plus omega square into a. And at a time t equal to 1 period, the acceleration is 0. Now you look at the first graph and the third graph. In the first graph, whenever the displacement is 0, acceleration also is 0. Whenever the displacement is positive maximum, the acceleration is negative maximum. And again, here both are attaining 0. Then here, when the displacement is negative maximum, acceleration is what? A positive maximum. Again, they are attaining 0. Are they directly proportional to each other or not? They are directly proportional to each other. Understand? So, we defined what is the definition of simple harmonic motion we have given at the beginning of this chapter. When is the motion of a body said to be simple harmonic? Whenever the body moves in such a way that its displacement is directly proportional to acceleration and in the opposite direction. Okay? So, from these two you find that the displacement and acceleration are directly proportional to each other and also opposite direction. You see here, d square by d square and y, the displacement and acceleration are directly proportional to each other, but with a negative sign, indicates that they are oppositely directed. So from this we confirm that the projection of uniform circular motion on any diameter is simple harmonic. Have you all understood? Okay, I hope you must have understood well. Fine.